who is ZoomAFM.com. We are basically a team of engineers and scientists, and we are basically former employees of Agilent Technology and then Keysight Technology. Some of us date all the way back to molecular imaging. At the first 2 weeks of our presentation, we have myself, Sang, Steve Raba, who is a service engineer of Agilent Technology. He can do all the repairs. XQ Tong, he was the technical manager of Agilent Technology, and then very important part of it. And then after the first 2 weeks, we have Gerald Carter joined us. He was former application scientist of Agilent Technology in Germany. And then we have Louis Pacheco, and Louis Pacheco is a former application engineer in France. And then later on, he invented his own imaging modes. And then when Agilent was no longer making AFMs, and then Louis Pacheco will continue to design his own instrument. Later on, I will show you some of his solutions. And while we are here, we want to keep your instrument running for another 10 years. That's the big goal. And we have application scientists help you, teach you how to operate the instrument. And I have an AFM set up in my own room and in my own basement. And then we're going to do some live demos so you can actually learn some of the basic operations. I'm going to support you and do repair and maintenance. Yeah. These are the initial part of the ZoomAFM, and it was made of nanocube technology, which is my business. And I invent a lot of other things. Later we'll talk about it. And then the HomeQ SPM Service LLC was formed by Steve Raba, and he was a former service engineer and a production engineer. So he actually is capable of building this instrument, some of the parts by himself, and he can fix things. Basics of AFM number 3, and about tapping mode this time. So again, we will show you the basic concepts of oscillations, dampings, changing of resonant frequencies, and at the end, we'll show you some simulations. Force interaction of AC mode or tapping mode, could AC or tapping. So when you have two objects close to each other, when they're very close to each other and they start to interact, and depends on how the interaction is, you could have, we could tapping mode. Basically, you have the tip that tap, or in other words, getting into the repulsive region of the interaction. Or you could also engage the sample at the non-contact, where the probe does not actually physically get into repulsive region, so attractive region. There will be a lot of discussion on what is attractive and repulsive. We only have 20 minutes, so we just started the basics. So we have the tip that tap into the sample. And here, I'm exaggerating a little bit, the tip is actually sink into the sample because at the moment of tap, the tip's getting to the repulsive region. And you use that way to measure the force. And then there's many different kinds of force. You can use it to be detected and then to image. Okay, so this is a repeat of last time that when tip is getting to around 10 nanometer of distance, it's going to experiencing a long-range attractive force. This is a result from the van der Waals force. And the force getting very strong when you get within 1 nanometer. And then it quickly switches to repulsive when it's when tip and sample is invading each other. Okay, so here you can see the tip is actually go into the sample, and then the force is quickly turned into a very strong repulsive. Okay. So the tapping mode use the oscillation of a cantilever to as a feedback signal to image. So to understand that, we're going to start with the oscillator. So the cantilever oscillation, basically it is a oscillator which made of a mass and a spring. Okay, so the simple oscillation theory tells us the frequency is K over M. K is the spring constant. M is the mass. You have a bigger mass, the oscillation resonant frequency goes lower. If you have a bigger spring constant or stiffer spring, the resonant frequency goes higher. So that's a simple formula. Okay. Now, when tip is getting into the sample, there's many things happening, and it's actually is a little bit more complicated than a simple oscillator. Here we have a spring, of course, and we also, because we're not in vacuum, we also have a damping. Okay, here's a damping. The cantilever will have certain friction to the air. That's why the resonant frequency is not a singular frequency. It's a little broad because of the damping. And then if you're imaging something in liquid, this damping is more serious. Okay, so that's the natural spring and damping. And when tips get into the sample interaction, when tips getting into this the surface, you add this system another spring and damping. Another spring is the repulsive and attractive force from your sample surface. Okay, so you have added another spring. This spring could lower the entire spring or increase the entire spring.
Thank you.
Yeah, it depends on whether you are into the attractive repulsive region. Okay, and then when tips get into sample, really interact with the sample in the repulsive region, you add another damping. You have spring and damping, so the entire system becomes a little bit more complicated. So, okay, that's the reality. And this actually, the change of spring and change in damping caused the resonance of the system to change. And that's the basics of tapping mode, basically, that the interaction spring and the damping from the sample change the entire spring and damping. Okay, see what happened to the resonant frequency here. Here, omega is omega 0, which is the system operation, which is the resonant of the cantilever without consideration of spring damping, and then it actually decreases with another the B, it's damping itself. So the damping is actually will cause the resonant frequency, as you can see, actually shift gradually to the lower. So the damping not only cause this resonance to decrease, right? When you have something damping it, the resonance peak start broad because you're losing energy. Not only that, it also causes your resonant frequency to slightly shift to the left. So imagine you have a cantilever, and as you close to the tip, close to the sample, the damping from the sample causes the peak to slightly shift to the left, and then cause the resonant oscillation amplitude to decrease. That's very understandable. You try to wave a stick, and as the stick is stuck to a mud, your waving amplitude decreases. Okay, so let's put in another perspective that you have this red line, which is the resonance frequency with a certain damping. And as the tip interact with the sample, as you can see, the peak shift lower and shift to the left. It's actually shift to left first and then lower and broad. Okay, so remember that when you tune your AFM, you always put your tuning frequency on the left shoulder of the peak. And that's because when tips shift to the left, the peak shift to the left, your amplitude does not decrease. Only when it shift very left and then start to broaden lower, and then your amplitude start to decrease. That put your driving frequency slightly left shoulder of the resonant frequency for the purpose is that wait until tips actually really damp on a sample in a repulsive region, and then the amplitude start to decrease. That is to assure that you're imaging at the repulsive mode or tapping mode. But if you understand that, that tells you this is not a rule. You can always put your driving frequency on the right shoulder of the peak. Okay, imagine you put the right shoulder of the peak. As soon as the peak shift to the left, the right shoulder start to drop down, and then you're actually engaging in the attractive region. So I will keep saying that and keep repeating that in the future presentations so you understand how do you control the tip sample interaction in the attractive or repulsive. However, in the first time you want to image or you're not very into AFM, very high resolution yet, You don't have to get too deep into it. Okay, here's another look of it. So you have attractive force and you have repulsive force. And here I take another look at that. When tip and sample in attractive region, the peak shifts to the left. When they go to repulsive region, because it increases spring constant of system, the peak shifts to the right. It is the first shift to the left and shift to the right. As it shifts to left or right, the height of the peak always decreases because of the surface damping that interact between tip and sample. Okay. So that is the basic physics of how we use the surface damping to changing the oscillation amplitude of the tip. So people always ask me this question in the middle of Q&A. They always ask, what is amplitude and why this image looks this and that? What is amplitude? Well, amplitude is exactly what does it mean? It is the amplitude of the vibration of the cantilever. Okay, that's exactly what it is. It's the oscillation amplitude of the cantilever. Okay, so I'm going to skip these. This slides is to explain how do you use this mode imaging long range force. That's not the focus. Force gradient, we already talked about it, and just make this slides a little bit bigger. And then as you can see, look at the peak when the tip and sample on the left. So when the tip and sample getting into attractor region, the peak shift to left. And then if you put the driving amplitude right on the peak, it will decrease. So imagine you put your driving amplitude, driving frequency right at the peak. As soon as the tip senses the attractive force, it decreases. And if your set point is, let's say 90%, it decreases, it immediately engages. And then that's how we call the tip and sample engage at attractive force. Okay. And then when if tips switch to the right, then you'll go engage in the repulsive force. It depends on how do you put the set point. And we'll not go too deep into that, just so you know as the base of the knowledge. Okay, look at how tip and sample engage. So these lines that represents the oscillation of the cantilever, and then it oscillate up and down. Here I use a simplified model where as soon as the tip and sample engage, the amplitude will decrease as the tip is pushing into the sample. Okay. In reality, it actually depends on where you put your driving frequency. It might increase a little bit and then decrease. It's actually more complicated than that. We just look at simplified. All right. Knowing that the amplitude, vibration amplitude of the cantilever will actually decrease as the tip go into your sample. If I put my set point right here and then use the difference, the error, which is the difference between the measured amplitude and your set point. Just use this number and use as feedback. We could maintain the engage between tip and sample at a percentage of amplitude. So that answers the question that a lot of people have is, how do I change the set point? So first of all, in tapping mode, your set point always need to be set at a percentage of free amplitude. So you need to know your free amplitude, right? So how do you need your free amplitude? You have to write it down or remember what's the amplitude number on your display box when tip and sample is not engaged. Okay, when tip is not engaged. And then if there's 5 volts, and then your set point should be like 4 volts. However, the instrument will automatically determine your set point. So you just have to remember what is the free amplitude, and then the imaging set point should be a percentage of that. You cannot make it higher than the free amplitude. Then tip and sample will not engage. Okay. So on the upper right hand corner, you see the white part. Suppose that is your topography. And tip is oscillating up and down, right? So as tip interacts with the sample, tip oscillate up and down. When tip is getting to a hole, a trench, a ditch, a lower point of sample, as you can see, the amplitude will go higher because the system allow you to oscillate higher, right? In other words, the tip is oscillating. The amplitude is, let's say, above is higher than your set point, and then the computer will calculate the error. Again, here the error when it's higher, the error is higher, and it will do integration, and then it will try to push the tip down to decrease the amplitude. Okay, you push it down. So that's where this part is. Push it down. When tip is scanning at higher point of the sample, high amplitude, right here, higher. When sample is getting higher, taller here, a bump, the oscillation of the cantilever is restricted, and therefore it'd be lower. Okay, it'd be lower. When the oscillation is lower, and we use this feedback signal right here, and feedback output back into scanner, it will try to lift the tip. So the feedback is try to maintain a zero difference between your amplitude and your set point. When you try to do that, it'll essentially track the height of the scanner, of the Z scanner, which have a tip on it, track it up and down of your sample. Okay, so the feedback output mimics the topography of your sample. When you have a bump, the scanner will lift. When you have a ditch, the scanner will drop. The scanner Z will go up and down according to your sample topography. Okay, that's how the tapping mode works. And in tapping mode, the set point is determined opposite of a contact mode. Last week we talked about contact mode. In tapping mode, when you reduce your set point, that means you're pushing the tip down, allow it to oscillate less, or allow to have more energies is applied to the sample. Okay. In other words, in tapping mode, lower your set point is equivalent to increase the force. Never lower down to zero, because if you lower down the set point to zero, it will never get to zero. So the scanner will keep pushing down until the tip is crashed to the sample. Okay. This is amplitude error, and then lower the feedback output. The feedback output is the high voltage of which mimics the shape of topography, and therefore in AFM control electronics, we'll call it topography. Now, before I finish, I'll talk about one more concept of this tapping mode imaging, which is the face. And in operating AFM, you always have face image. And what is a face image? Face image is the difference in timing between the driving signal and your actual oscillation of the cantilever. You drive at this timing, your cantilever is actually oscillated up and down at a slightly delay of the driving signal timing. Okay, and this slight delay is represented by the shifting of the resonant frequency, and actually will show you the mechanical property difference. Here is the schematics. It shows you that when tip is tapped into a soft sample or more damping sample, and this soft sample not only cause the image amplitude to change, but also cause the tip lose more energy on the sample, and therefore cause a more delay of the phase. And if we plot the phase delay of all these your imaging, you have the phase image, and this phase image represents the mechanical property of your sample. Of course, sometimes it's always coupled a little bit with the topography, because as you can see, if tip is climbing a mountain or walking down a mountain, the damping is also different. So yes, the phase imaging is more complicated, and the scientists try to make sense of phase. And what exactly phase? Can we call it a softness? No, we cannot. It's actually, phase is impacted by a lot of factors, including the softness, including the damping, and including the slope. That's why when we do phase imaging, that when the scientists invent this phase imaging, they just give up the idea of try to directly link to a physics property. So they just call it phase, and then we just say it's a phase image. Before I stop, I'm going to show you a model, because this is the thank you notes now. I'll show you a model. It's just very interesting and very intuitive. And then stop sharing this and then share this program of my, give me a second. Stop sharing and share this program. Again, I'm going to try to make these programs available for you to download. And because I don't own these, and I get it from someone else anyways. And thanks for Joseph Griffin of AFM Lehigh Micro School in 2003 from NC State. And he basically said, hey, go ahead and download it and teach in your class. So here is a model of us oscillator. So let's oscillate. Okay, so now we have a driver, which is the blue part. Okay, and we have an oscillator, which is the red part. When you drive a certain frequency, a lower than its resonant frequency, you can see this two vibration has the same timing, almost the same. When we say the same timing, we call it we have a zero phase lag. The phase lag is zero. Okay. Yeah, let me reduce the damping. Zero phase. And when your damping is very low, even somewhere all the way very close to the resonant frequency, the phase lag is also very close to zero. This is actually, let's end this. Oops. Let me try to do this one more time. Okay, I accidentally clicked the stop and then you stopped it. Let me try to do one more time. So here again, I'm going to reduce the damping and put linear resonant frequency and go. Okay, you can see that the driving timing and oscillation timing is actually very close to each other. Now, what if I go very near the resonant frequency? Let's here, see right here, and put a little damping here. Okay, now something interesting happens. As you can see, the driving timing and the actual oscillation timing started to have a difference. This difference is actually what we call the phase lagging, the delay of timing of this oscillation. That's phase, and depends on where do you put the driving. This phase lagging can be very different. If you drive very high, it could be we call it complete out of phase. Okay, and this phase lagging is impacted by a lot of factors, including damping. You have a lot of damping, the phase is getting lower, or the damping effects cause the phase to delay more. Or if you have less damping, it will delay less. So as you can see, if you're already confused about what is the interaction between them, how do we estimate? Then you're right, you're confused, and then it's very confusing because it is actually impacted by many other factors, including damping, including where you put your driving frequency, and so on and so forth. So if you wanted to really chase what is exactly phase, there's a lot of topics, research topics about it. At this point, you just have to understand phase image represents the mechanical environment of the tip and sample. And then when you have two materials which has different type of which have different type of phase or mechanical property, then the phase will show a difference, and that's called the phase lag. Okay, so we're near the bottom of the 30 minutes, and I'm going to turn back to my PowerPoint and then give you the last couple of slides. Okay, so yes, we try to do every Tuesday morning, but I also had the feedback that Tuesday morning may not be the best time for everybody. So I'm thinking with the exact same material, I could also repeat this material on Monday afternoon. I'm thinking about 3 p.m. and I'd like you to email me see is that a great idea or whatever it is, and then send to support@zoomafm.com. We're going to read your email, any feedbacks, any questions, problems. This way, I'm going to make it works better and benefit more people. And next week, I'm thinking about back to the basics. Look at the live instrument. I have an AFM set up in my office. We're going to try to do live demo. Basically, put a sample there, and we'll share the screen, and then you can actually see what's happening. So it's more like a demonstration, less like a presentation. These are the members of this platform. NanoSQ technology is, I invent a lot of things and it's on it. OnQ is the repair service. And we have another website, another company joining is CS Instrument. And then this is the company that started by a former engineer, application engineer of Agilent Technologies named Luis Pacheco. And he has figured out a way to build, design a controller that can replace the old controller and computer and drive the old instrument, which is it's a great idea that you can make an old instrument live. Not only that, you can drive old vehicle instrument, and he has his own AFM too. And if you're interested, again, send us an email, and we'll talk about it, and then I can send you more price quote and so on and so forth. All right, this is it, and I'd like to open the floor for questions. And you can go ahead and unmute yourself. And then, yes, I'll try my best to answer your question.
Hey, Song, I have a question about a particular sample that I'm trying to image. It's a much softer substrate that I'm usually working with. It's aluminum tape. And I was wondering if that tip that you were giving about changing which side of the shoulder that you're on would be helpful for that.
Aluminum tape, right?
Yeah.
Are you imaging aluminum or are you imaging the sticky tape?
It's aerosol particles that are impacted onto the aluminum tape, but like that's the substrate. So it's pretty soft.
Okay. Yes, this is not a difficult sample. The only concern is that if you are doing very repulsive tapping mode imaging, I mean, very repulsive, the aerosol may have some loose particles that are attached to your tip. It might make your tip big or sticky. That's the only concern. So the rule of thumb is that you should image with minimal amount of force that is stable. But that is very hard to achieve because you don't know what is the minimum amount of force, and you actually don't know what the imaging resolution you can achieve. So it's always a guesswork. The approach, when I approach an unknown sample, I always drive it at a lower amplitude and gradually increase your amplitude. That's one way to do that. You can always use high amplitude and then reduce. But remember that when you use high amplitude, when you reduce, if there's negative effect to the tip, you cannot go back. Your tip is already changed. Okay. So this is still too complicated to follow. What I suggest is that in your instrument, you could set your target amplitude to be lower. You know, normally when I'm doing the experiment with someone else, I'll set up 5 volts because I can click and it automatically work because tapping mode is so easy. But to protect tip, you should reduce your amplitude. Let's say reduce to 1 volt. So when you auto tune it, you reduce to 1 volt. But what if your amplitude is already 5 volts or 7, 8 volts? You can reduce your drive so your amplitude is 1 volt. I'm thinking 1 volt on your sample is probably gentle enough for you to image your sample. Yeah, I don't find your sample is particularly difficult. It seems to be tolerate a lot of difference in parameters, but to protect the tip, you should always use like a median amplitude, not very low. Very low means like 0.5 volts, 0.2 volts. Median is 1 volt. It's probably good enough.
Great, thanks.
Now, if you cannot achieve a stable engage, let's say that no matter how do you adjust your gain, I gain, it keep oscillating, then you can always increase your drive. The way to increase it is you increase your set point to maximum, let's say 10 volts, So tip will lift. And then you increase drive a little bit and you watch the amplitude. If it increase from, let's say, 1 volt to 3 volts, and then you type in 2.5 volts as a set point and engage again. I think next week I can try to set up an instrument so I can actually show you how to do that. Okay, so that answer your question.
Hello, Dr. Song.
Yes. What's your question?
So we have an instrument like AFM, which we use for recognition imaging, and I think the closed loop, AC closed loop of that system is not working. I think the auxiliary board is broken, I guess. So do you think we can get it repaired?
Yes, anything can be replaced and repaired. Why don't you send the email to support@zoomafm.com, and I can talk to individual one-on-one so we can figure that out.
Okay, and also we have like two systems. The other system which we have is the head electronic box, which has like A and B, which shows like 9.88 or 9.9 some reading. So it's not showing the reading what it is supposed to be. And we don't know what is causing it. Even if there is like no sample, no scanner, it shows like the laser point is still showing up.
So you have two instruments, and are they of the same model?
Yes, yeah,
Okay.
the Pico
So
Plus, yes.
I'd like you to make sure you really narrow down the problem by switching parts, right? If you think the head electronics has problem, you switched with the other head electronic box, just switch it to see does it make the problem go away. Just using common sense to narrow down the purpose of your problem.
Okay.
And then you write a complete diagnosis of email, including pictures and everything, and
Okay.
send to me, send to us, support@ ZoomAFM.com, and I will connect you to our application scientists who can do the repair.
Okay. Yeah,
Where are you
got it.
located? Just curious.
I'm from University of Georgia, Athens.
Georgia, Athens. Yes, yes, I know where it is. I installed that system many years ago. I know that I used to live in downtown Georgia, and it's walking distance for me.
Okay. Yeah. So I'll try to diagnose what causing it, and then I'll send you an email.
Yes, yes. You switch it and you narrow it down, because here's the rule of diagnose any problem is that when you do any kind of change, you're always changing one factor at a time. You don't want to switch the head electronics box same time, change the tip. You just change two things. Okay. You only change one thing at a time. You cannot change two things at a time. You can choose two things. You observe something. It could be your tip is bad or whatever it is, right? Always change one thing. And then you write a complete email.
Okay.
And then we'll connect you.
Oh, okay. Got it. Thank you very much.
Yeah, yeah.
Yeah, thank you.
Everybody else, I need input from you that is this Tuesday mornings good, and how many of you has better time suggestion? I'm thinking about Monday afternoon, 3 o'clock. If you have lots of meetings on morning, I've not decided yet, but this time is great because people from all around the world, including have a lot of time differences, could join in, but sometimes a compromise could be not convenient for some audiences. So do send me email about a good time suggestion. Okay, I'm waiting for more questions. You can also type in the chat box, and then yeah.
Hey, Song, it's Jason here. Just, another question, not related to the AC mode, but the thermal case. So, of course, I have a really old system. I have the old 4500, and I have the newer software, the PicoView 1.2, and I put a National Instruments card in there. The address that it's specifying, is this just would it be called like device 5, or I was kind of looking in the manual and I didn't see exactly like how the address should be written out.
Yeah, the Thermal K is a add-on. Basically, it's a national instrument board plugged into your computer, and the software reads that. I'm not expert on that, but I do know someone who knows a lot about it. Send me a complete description or email, screen capture. Again, I will connect you with the person who knows the answer.
Okay, awesome, thanks.
Yeah.
I guess if no one else asks, just another curiosity question. The amplitude distance curves. I've just noticed like over the years how you can kind of get different shapes and outputs from it. And sometimes I find, of course, it changes as your tip ages and stuff like that. And are there any sort of rules of thumb with
yes,
observing them?
yes, of course. There's lots of them, and I have like 2 hours of lecture just about it. And this is actually, and not only you can do amplitude distance curve, you can also do phase distance curve, and then that tells you a lot about what kind of force between tip and sample. There is tons of stuff there. I need 2 more hours of your time.
Yeah.
Yes. So when you approach the tip sample, let me try to explain it as much as I can within these slides I have it today. Okay, so this is amplitude, and as you tip, if you put the driving frequency right here, right, as the tip engages to sample, okay, the peak is going to shift to left. As you shift to left, it's actually past the driving amplitude, right? When it passes the driving amplitude, you can see the amplitude actually increase a bit, slightly increase, just bump up a bit, okay, and then as the tip go further into the sample, it's going to drop down, right? So you can have a little bump there. It's kind of hard to tell. However, when you do amplitude distance curve and you also plot the phase distance curve at the same time, then you know what this has come from, because the phase shift caused by the shifting of the resonant frequency and the increase of damping, they probably behave a little bit different. So at that moment, I have another presentation just basically tells you the phase distance curve. It's actually look like a force distance curve, because think about it, in contact mode, you can do force distance curve, right? The force distance. How do you do force distance curve in amplitude? In tapping mode, you can actually do it too. Okay, there is a very smart guy in Vico. He actually did that experiment. What he did is that when he does tapping mode, he does force amplitude distance curve. At the same time, he does this exact amplitude distance curve on another cantilever with a laser shine on it. So he can measure that force, which tells you a lot about the attractive repulsive force during the amplitude distance curve. That's an interesting way to look at it. Of course, I mean, it's difficult for you to do a force curve of one tip on another tip. But yes, and then actually he draw a lot of conclusion from it, that your control, your force is totally depends on, surprise, the drive. And then if you look at all the manuals from all the AFM companies, nobody talk about drive. They say turn, and they say put your driving frequency to the left shoulder. That's all they say. And why is that? Nobody explains it. And why you put the target amplitude as 1 volts as compared to 8 volts? What difference does it make? It actually makes huge difference in force, engaged force between tip and sample. And then, yes, I will cover that in a more advanced part of it. And then it basically tells you that you can completely manipulate the engaged force and reach the best resolution you can get by the minimum amount of force stable. That's what it is, minimum amount of force stable. Okay, when the force is too low, it's not stable in the attractor region, typical in and out. It's not very stable. Yes, it's a good question, and yes, it takes more time to explain it. Well, if we don't have any further questions, I'm going to thank you for today's time. And hopefully you forward this ZoomAFM.com. I will email you more and then forward to more people. And we'll see you next week. And next week, I'm going to do live demo of my instrument. And I can show you how change these parameters and how does it impact your force. Yeah. Thank you for your time. And then if you want to stay a little bit, ask my questions, you can go ahead. I will stay here for another 20 minutes.
Hey, Song, I do have an appointment I've got to get to, so I'm going to go ahead and drop off if there's no further questions, okay?
All right. Yes. Okay. Talk to you later.
Have a good day, guys.
Good day.
Hi, Dr. Su. This is Karen. Um, so regarding the email that you sent me yesterday about the controller that maybe you have an idea of what's the problem. Do you think we can go through that?
Yes, that I asked the service engineer about this problem of the extra noise. Look, I've seen it several times.
Mm-hmm.
And it could be the power supply has imbalanced plus and minus voltage, which impact the amplifier, which is a little beyond my knowledge. And yes, if I can duplicate the same problem on my controller, I have several old controllers. If I can locate the cause, then we should have a solution.
So what can we do? I mean, do you need me to send you something like pictures or you
Yes,
can
I probably
try?
already know it, but you could send me some pictures of latest. And
Okay.
yeah, that's just keep that problem alive. I used to have no idea. I thought it was the Mac AC box problem, but then one of the engineers say maybe your preamplifier has imbalanced input of voltage. We have a plus minus 15 volts, and these two voltage are slightly different. The amplifier will hop between the two modes, cause the same noise.
Okay, so
I'll
maybe
forward
we
it
don't
to
need.
Steve Raba, and then he's an expert, and he can probably tell me what to do.
Okay, so basically maybe we don't need to change the controller. Is that right?
Maybe we don't need to. That's correct. Yes, if we can
Okay.
change the one part, that fixes the problem.
Okay, so I'll try to take the like pictures of the issue and I'm gonna send you an email
Right. Yes.
later. Thank you so much.
Okay. Okay. No questions. I'm going to stop the recording.